everybody, and welcome to this lecture video for Tuesday, November 6th of 2018. I want to apologize for not being there in person with you. I've had a family member have an emergency who's having some emergency surgery tomorrow, so I am not able to be there. But I will be there on Thursday to answer any questions that you have on this video. So this video is not optional. It takes the place of lecture, and there will be some things to turn in on Thursday. So on last Thursday, we started section 4.6, which is applied optimization, and I want to just recap what the steps are to applied optimization. I know we didn't work any problems yet, but we talked about the steps in class. So first step when doing an applied optimization problem is going to be just to read the problem. So, then after that, you're going to draw a picture. I'm a terrible artist, so you're going to see some of my terrible pictures today. You'll introduce variables, write an equation for the unknown quantity in terms of a single variable. So this means that we're going to write it in terms of just x or in terms of just y. Then we're going to look for the critical points and the endpoints in any particular domain. Sometimes you have to test them all, sometimes you don't, and we will figure out what the actual either maximum or minimum of the particular applied problem is. Now, if we've got more than one, so if we've got more than one critical value within a problem, then we can use the second derivative test to see if it's a maximum or a min. So remember that if it's an absolute maximum if the second derivative is negative, an absolute minimum if the second derivative is positive. So this is like a recap of what we went over the other day. We also wrote a bunch of formulas. So if you don't have those in front of you, take a look on e-learning because that list is there, listed as 4.6 part 1. So I want to talk about some applied problems. And these are, you can print these out off of e-learning, and there are 3 of them that we are going to work on partly today. So for example, the first one says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So his goal is to maximize the area. If I want to figure out how to maximize the area given a function, then we're talking about a rectangular field, and it borders a river. So bordering a river on one side, I'm going to draw in what we're actually looking at. So if it borders a river on one side, then it has 3 sides that we have to fence. And I know that doesn't look like a wavy river, but we'll call this the river border, where we don't actually have to put fencing. So part 2 on our applied optimization problems is just to get an idea of what we're looking at. So here is our rectangular area, and just by the way it's oriented, I'm going to call this x and this y. And there are a couple of formulas that have to do with perimeter of a rectangle and area of a rectangle. So if I'm dealing with area is equal to the length times the width. And in this one, the area would be equal to x times y. So length times width. I've set it up with x and y. If you want to label it L and W, you certainly can. The other thing that we have to do with, and this is the thing we want to maximize, the other thing that we have to do with is the perimeter. So the perimeter normally for a rectangle is 2 times the length plus 2 times the width. Except for our rectangle, we don't have to worry about the river side. So this one is for our situation. This is the normal one. For our situation, we're going to be dealing with 2 times the width, or 2x. And we're dealing with 1 times the length. So we only have 1 single length. So 2x plus y. We also know that the farmer has 2,400 feet of fencing. So this perimeter is going to equal 2,400 feet. So that's a piece that we know. 2x plus y is equal to 2,400 feet. Now, we know what we want to maximize. We know we have a relationship that has to do with the perimeter. But you notice that both of those equations are in terms of x and y currently. So part 4 in our instructions is to write in terms of a single variable. Now, if I want to write this in terms of a single variable, I can pretty easily solve this equation for y. So solving that equation for y would be equal to 2,400 minus 2x. So really, if you think about it in terms of applied problems, whatever we have left to spend on this particular part of the fence is the whole fencing, so the whole 2,400 minus what we put here and here. So that's a way to express y in terms of x. Now what we can do now, since we want to actually maximize this piece, is we can substitute out that y with what we know it equals in terms of x. So substituting, then I know that the area is equal to x times y, which is 2,400 minus 2x. And then we can simplify that out. Area is equal to negative 2x squared. I'm just distributing the x, plus 2,400x. So distributing the x here. I also put the terms in order just because we want it in descending order. So this is what it actually looks like. Now, if we want to think about what domains are valid, we can have x values up to what doesn't make a perimeter anymore. So I've got 2,400 feet of fencing. So the longest that this length could possibly be would be 1,200, because this one would be the same length. And essentially that means that y would be like tiny, 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 wouldn't actually make a perimeter at all. But the smallest that x could be, it could be essentially 0. So I could have a really long, narrow field where this thing goes to 0, and what I have is a little strip along the river at that point. So either I have a really deep one where the x values are really long, up to 1,200, or I have a little sliver of x and I have a really long thing along the river. Those are my two bounds in my domain. So 0 has to be less than equal to x, has to be less than equal to 1,200. Now, at both of those endpoints, at 0 and 1,200, I don't really have a field anymore. So those are really on the outside of our bounds. Hopefully we can find a critical point in the middle that we can use. So now we're about maximization, which is part 5. And now I'm going to, in order to maximize, I need to look for my critical points. Any critical points that are outside the 0 to 1,200 I can throw away because they don't make sense in terms of the problem. They'll still be critical points of this equation, but they don't make sense in terms of the problem. So solving that, a prime would be equal to negative 4x plus 2,400. And if I want to set that equal to 0, negative 4x plus 2,400, moving 2,400 over, dividing through by negative 4, we get 600 is equal to x. All right, now we need to make sure that that's within our domain, and check it is. So we have one critical point here, and that's at x is equal to 600. Now if I were to consider the second derivative, so d2a dx2, then we're taking the derivative of a prime, so a double prime gives me just negative 4. This is always negative. Which means that our critical point is a max. All right, so what are the dimensions of the field that has the largest, I didn't even notice that T was missing, the largest area? So we haven't really answered the question, except we found that 600 is our X value. We still have to figure out what our Y value is. So Y is equal to 2, negative 2X plus 2400. So Y is equal to negative 2 times 600 plus 2400, giving us Y is equal to 1200. So X is equal to 600, Y is equal to 1200, and then our maximum area would be equal to 600 times 1200. And if we use the trick of multiplying just the numbers, 6 times 12 gives us 72, and we end up with all the zeros. And it's in square feet for our maximum. So here we get an idea of one of our applied problems. Now this is one that works with just, oops, missed a zero. This is one that works with just a rectangle, where we're maximizing a rectangle. We don't always deal with just rectangles, so I want to do one that's a little bit more challenging. So if we are working on a different type of equation, let me find my rest of my notebook. Aha, here we go. A man launches his boat from point A on a bank of a straight river, 3 kilometers wide, and wants to reach point B, which is 8 kilometers downstream on the opposite bank, as quickly as possible. He could row directly to B, or he could row to some point D in between C and B, and then run to B. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land in order to reach B as soon as possible? We assume the speed of the water is negligible compared with the speed at which the man rows. So we have to figure out how far this distance X is that this person is going to land on this riverbank in order to get, he's starting at A and he's trying to get to B as quickly as possible. So he could go straight across the 3 kilometers, and he could travel the 8 kilometers all the way down the side of the river, or he could cut it at an angle and hit a point in between and then just have to run part of the way. So our job is to see what way it is to make it as easy as, or as quick as possible. So a couple of things to know is that the time it takes to get somewhere is always the distance that you travel divided by the rate that it takes you to get there. So if I'm looking for the total time, then the total time is the amount of time it takes him to get from A to D. So I'm going to say, we'll call that T from A to D, plus the amount of time it takes him to get from D to B. Now, it could be that that distance X is equal to 0, in which case the letter D actually becomes the letter C. That's not out of the realm of possibility. In fact, if we're considering a domain, then 0 is less than equal to X, which is less than equal to 8. So it could be that that X distance is approaching 0 or approaching C. It could also be that that X distance is approaching B. Now, other things that I want you to notice is that we know some things about the dimensions of this particular path. So what I'm really looking for, we have this side of what you can see is a right triangle. So I know that this side here is 3 kilometers. I know that this side here is equal to x. So we can actually figure out the length of that hypotenuse. So by the Pythagorean theorem, a squared plus b squared is equal to c squared, with c being our hypotenuse, then we know that 9 plus x squared is equal to c squared, which gives me that the length of this side is the square root of 9 plus x squared. So I want you to note first that the square root of 9 plus x squared is not 3 plus x, so do not try and simplify it that way. As soon as we have a plus in there, we cannot do that. So now I want to set up my actual time formula. So here time is equal to the distance, and the distance for this first piece is this length from A to D. So the distance here is the square root of 9 plus x squared divided by the rate. Now it says that he can row 6 kilometers per hour. So here, 6 kilometers per hour. This distance up here is in kilometers. And then we're going to add the remaining distance. Now, if I'm thinking about the remaining distance, the whole length of this thing is 8 kilometers. So if I'm trying to set up what's left from point D to point B, then however far we travel x has to be subtracted from that 8. So 8 minus x is the length of that distance from D to B. So here on the top, I have 8 minus x, and it says that he can run 8 kilometers per hour. So 8 kilometers per hour, and this is equal to kilometers. All right, if we simplify this a little bit, because right now it looks a little intimidating to take a derivative of, so if we're going to simplify this a little bit, I would probably write it as 1/6 times the square root of 9 plus x squared, and plus, I can divide 8 into both of these things, so and we have 8 over 8, which gives me 1, minus 1 over 8 times x. So last simplification, 1/6. I'm going to write it in a form we can take the derivative. So 9 plus x squared to the 1/2 power plus 1 minus 1/8 x. All right, we are working on maximizing this thing, so we need to take a derivative. So dt dx is equal to, bringing the 1/2 down, I get 1 over 12 times 9 plus x squared to the negative 1/2 power times the derivative of the inside, so times 2x. And the 1 goes to 0 because it's a constant, and then I have minus 1/8. All right, cleaning that up, dt dx is equal to 2x on the top times 12 times the square root of 9 plus x squared on the bottom minus 1/8, and that's what we have. All right, now working through my derivative, if I want to find the actual maximum value, then I need to set that equal to 0. If I'm setting this equal to 0, then I have 0, this is for my critical points, I have 0 equal to, let's simplify this into 1/6. So x over 6 times the square root of 9 plus x squared minus 1/8. Bringing the 1/8 to the other side, I get 1 over 8 equal to x over 6 times the square root of 9 plus x squared. And then I'm going to cross multiply in order to solve. So 8x is equal to 6 times the square root of 9 plus x squared. In order to solve the thing, I need to bring everything but the square root to one side so that I can square both sides and cancel that square root. So dividing through by 6, I end up with 4/3 x equal to the square root of 9 plus x squared. And squaring both sides, I end up with 16/9 x squared equal to 9 plus x squared. Bringing all of my x terms to one side, 16/9 x squared minus 9/9 x squared gives me 7/9 x squared equal to 9. And then multiplying by 9/7, so times 9/7 on both sides, gives me x squared equal to 81/7, and taking the square root of both sides, x is equal to 9 over the square root of 7. Now normally when you take the square root of a variable, you end up with the plus or minus case, but we're talking about a distance. So this is a distance, which means that we can only have a positive value, and this person, in order to maximize or minimize the time that it takes for us to get there, would need to travel this distance in order to down the bank. So it'd have to be positive. If we want to make sure that it's somewhere between 0 and 8, I cannot visualize 9 over the square root of 7, so 9 divided by the square root of 7 gives me 9 divided by the square root of 7, 3.4 as far as our distance is concerned. Now if I want to know how long it actually takes for the person to get there, then I can plug that back into my time equation in order to figure out how long it actually takes. So t of, I'm going to use the decimal form, 3.4, is equal to 9 plus 3.4 squared over 6 plus 8 minus 3.4 all over 8, and 9 plus the square root of 9 plus 3.4 squared all divided by 6 plus 8 minus 3.4, not 304, 3.4 divided by 8 gives me 1.33 hours to arrive. Note that for these applied problems, I will allow you to use a regular non-graphing calculator for these, so you will have that ability. All right, so moving to the next problem. This says you're tasked with designing a cylindrical can to hold a new soda beverage. This can must hold 355 cubic centimeters of liquid. It has been estimated that the side of the can will cost 5 cents per centimeter squared, and the top and bottom will cost 10 cents per centimeter squared. Find the dimensions that will minimize the cost. All right, so this is your challenge. This is, you can start earning bonus for test number 3 here. And my intention was to actually give this to you on Thursday as a bonus, but we didn't get this far. So this is bonus for test number 3, due next Tuesday. On the 11/14, 13, not 14. If you want to have a printout of this that you don't have to print yourself, I will have this in class. On Thursday. There is one that is very similar to this in the textbook as an example, so you can follow the guide of that. You will have to set up the equations yourself. You're more than welcome to work together on it as well, but this is a problem that's going to be a bonus for the next test. So I am going to stop the video here, and I will record a second video. I just want this to be in small, manageable pieces. So second video coming up, and stay tuned.